Hi, my name is Anna Jung, and this is my creative assignment number 3, titled Real World Moments of Inertia lecture. So, some background for our lecture. What is a moment of inertia? So here I provided our dictionary definition from Merriam-Webster of what a moment of inertia is, but essentially a moment of inertia is a measurement of the resistance of a body to angular acceleration. So essentially your resistance to rotation. I provided you some general equations here where our moment of inertia is essentially equal to our mass um, times our distance squared, distance to the axis of rotation. So I've got it in the integral form, and then also we've got our summation form. I've also provided here some shape-specific calculations for moment of inertia because your moment of inertia is heavily dependent on your center of mass, which varies on what shape you're dealing with. So we've got some hollow sphere, solid sphere, we've got some cylinders here, hollow cylinder, we've got some rods, some rectangular prisms. And our most popular units, and our SI unit specifically for moment of inertia, is kilogram meter squared, but since we live in the United States of America, you will also occasionally see some pound feet squared. The next piece of information we're going to talk about is the conservation of angular momentum. So what is the conservation of angular momentum? Well, a conservation property means equal or conserve, so things stay the same. So our initial angular momentum, which here is represented in our equation as Li, is going to be equal to our final angular momentum, which is represented here as Lf. So how exactly does this relate to moments of inertia and omega here, which is equal to the angular velocity? So we have I and then omega, which so our moment of inertia times our angular velocity, well, that is equal to your L, your angular momentum. And since we have our angular momentum conserved, we can say that the initial moment of inertia, which is I subscript I, multiplied by our initial angular velocity, which is omega I, is going to be equal to our final moment of inertia, which here is IF, times our final angular velocity, which here is represented as omega F. So getting into the meat and potatoes of our lecture today, we're going to go through our real world example number 1, a spinning ice skater. So I'm going to play this video and we're going to make some observations of this ice skater as she skates. So playing the video, we see our ice skater, she's got her arms stretched out and she's spinning, and slowly she brings her arms in and she starts spinning faster. So our observations that we're making. When the skater pulls her arms in, like she did there at the end, her angular velocity increases. So she rotates or she spins faster. So why does this happen? So when the skater pulls her arms in, her moment of inertia actually changes. So she's changing the distribution of her mass from her axis of rotation. So does the moment of inertia increase or decrease here? So given our conservation of angular momentum equations, we can see that our moment of inertia I and our angular velocity W are inversely proportional. So that means basically when one goes up, the other one's going to go down. So from our observation, we saw that as she brought her arms in, her angular velocity increased. So if our angular velocity is increasing, we can fairly deduce that our moment of inertia is decreasing. So our second real world example today is actually going to be about baseball bats. So I don't know if you guys are MLB fans, if you watch the World Series, watch the Yankees lose to the Dodgers, but the MLB, the Major League Baseball Association, they actually prohibit something called corked bats. So let's talk about why that is. What is a corked bat? So if you don't know, the MLB typically uses just plain old wooden bats. In a corked bat, what happens is they take a normal wooden bat and they drill a hole in the center of the bat, and they fill that hole either with nothing or typically with cork, which is a much lighter porous material. So how does this corking of the bat affect the bat's moment of inertia? So since they are drilling a hole in the bat and filling it with a lighter material, a material that's porous and has less mass, that will actually decrease the bat's moment of inertia. So would this be an advantage to the batter? Well, compared to a normal wooden bat, a corked bat will be lighter and have a smaller moment of inertia. And this lighter, smaller moment of inertia bat, it allows for a quote-unquote smoother swing and increased control. So as the batter brings the bat around to hit the pitch, it allows for a much smoother swing. It does not have as much resistance to that rotation as a normal bat would. So our final example for today, our real aerospace example, if you will be about rocket fuel consumption. Now, moment of inertia has a ginormous effect on the aerospace industry, coming from anywhere from determining fuel systems and how to place them throughout and distribute them throughout the mass of your system. Moments of inertia also affect your roll, your pitch, and your yaw of both aircraft, spacecraft, and even rotorcraft. So this is just one example that I'm picking out of probably hundreds that I could have done, but this is one we're going to stick with today. So what happens to the moment of inertia of the rocket shown here, or any rocket in general, as it burns fuel? And how does the change of the rocket's moment of inertia affect the rocket's dynamics? So generally speaking, compared to a rocket with a full fuel tank, let's try saying that 10 times fast, a rocket with a partially filled fuel tank will have a smaller moment of inertia. So as the rocket burns fuel, you're changing the distribution of the mass and the distance of that mass to the axis of rotation. And so as the moment of inertia decreases during the rocket's trajectory, the angular velocity of the rocket increases. So per, again, our conservation of angular momentum, as the moment of inertia decreases, our angular velocity has to increase in order to conserve that momentum. So this increase in our angular velocity could potentially destabilize a rocket. So there's a lot of analysis that goes into the design of fuel systems in rockets in order to account for the stability of the rocket and how to maintain that during the trajectory of the rocket. This concludes our lecture for today, so thank you for watching.